Welcome Engineering Statics. This is ENGR ampersand 214 at Bellingham Technical College. This lecture is going to involve what's called couples, and this is a special application of moment with no force. So the definition of a couple from the standpoint of engineering statics is a pair of forces equal in magnitude but having opposite directions and different lines of action. So several points. Got to be equal in magnitude, they got to be going opposite directions, and they can't be right on top of each other. They have to have different lines of action, so a separation radius between them is another way of saying that. The significance of these little arrangements is that they provide pure moment to the system, no net force. So if you were to say what's the sum of F2 or of negative F and F, excuse me, here on this figure, it would be 0. They cancel each other out completely. Now that said, because there's a separation distance between them, they create a torque around pretty much every point in the plane of the paper here and elsewhere. So that's what we'll be looking at with respect to couples. They're pure moment generators. And if we wanted to say, well, how much torque does it produce, or what is the magnitude of the moment due to the couple, you might have studied in physics that you could write a formula for that and say that this would be equal to the distance between them, d, shown here on the figure, between the dotted lines of action, and the magnitude of any one. Not both, just one. So the magnitude of the couple is equal to the distance between the two lines of force, the perpendicular distance, and the magnitude of either one or the other. Okay, so and then you're going to use the right hand rule to figure out which direction it's pointing in. And of course the moment due to the couple will be perpendicular to the plane that the two lines of action make. It's sometimes really easy to forget this formula. A lot of people tend to put a 2df in here. So it might be nice to kind of have a quick way to refresh ourselves on where this formula came from. And we're going to use the same kind of consideration we did in looking at the moment of a force about a line, and the same kind of vector algebra rationale that we did to prove it. Because if we can prove this, then, you know, if we do forget the formula, we can always rederive it and make sure we know what we're doing. And an order of magnitude, or a factor of 2 error is not as bad as an order of magnitude, but it's certainly not something we would want to turn in our first job. Okay, so let's just go ahead and calculate moment of these two forces separately, and let's just pick some point P in space here. Whatever. It's any point, right? We say the moment due to a couple should be independent of the point. So let's pick this point P, and let's extend the lines of force of the lines of action of the forces with these dotted lines, so we can draw some radius vectors. Okay, so we can write the moment due to positive F about P is just going to be some radius vector from P to the line of action. So let's use R P to B. This vector right here, R P to B cross F. Okay, R P to B cross F. And let's use some vector algebra to relate R P to B to R P to A and R A to B, because we're going to want to relate R P to B and the moment due to F to the moment due to negative F. So let's do our substitution up front, knowing we're going to need to do that. So we're going to substitute in for R P to B. We're going to do the vector sum R P to A plus R A to B. So here's our vector algebra again. We're just going to do a vector addition and substitute that. And then we're going to distribute our cross product. So we'll end up with R P to A cross F plus R A to B cross F. So this cross F plus that cross F. Okay. So let's take our other force, our negative F. So same magnitude going in the opposite direction. So we're going to get a radius from our point of interest to a point on the line of action of negative f, which is point A happens to be on the line of action of negative f here. So we'll have rp to a cross negative f. Remember, we can take a vector and write the algebraic inverse with just a negative sign, and now it's pointing in the opposite direction. So that's why we literally have a negative sign in front of f to denote that it's this vector. We didn't say anything about its line of action position, but we did say something about its direction. It's pointing in exactly the opposite direction of f. So this vector can be very accurately described as negative. This one, the negative of that one. Okay, so we can take the negative sign's a scalar, so we can distribute scalars over vector addition and any kind of multiplication all day long. So I'm going to factor this negative 1, scalar 1, out of this cross product and sit it right out here. Okay, so I know that the moment about point P due to this force plus the moment about point P due to this force is going to be the same as the moment of both of the forces put together about point P. So that was the moment of the sum is equal to the sum of the moments. Well, the moment of the sum is the couple moment. So I can say the moment due to f about P plus the moment due to negative f about P is, by definition, that's the moment of the couple, because those are the only two forces in the couple. So they should add up to the couple moment. So I can write that out and just substitute what I've done to express these two force moments about P, and just start substituting in. So the moment due to F about P is this right here. So I'm going to put that in, and then I'm going to subtract what I got for the moment due to negative F about point P, which is this right here. So there that is. Okay, so now I'm going to do some recognition here. Let's look and see if we got any terms we can cancel. Oh wow, check this out. RP to A cross F, RP to A cross F, negative. That goes away and that goes away. So I'm left with RAB cross F. Okay, what was RAB? Oh, right here, RAB. Hey, RAB is a radius vector that connects the two lines of force. What out? Okay, so I take this line, it's in a cross product with the line of force of F. Okay, so RA to B is this vector, and it's being crossed with F. So I'm going to go back to that geometrical definition of the cross product and say, well, I could write this as the magnitude of RAB times the magnitude of F times the magnitude of the sine of the angle between. What's the sine of the angle between? Right here. This is the angle between the two, the acute angle. Okay, the sine of that angle, though, times the magnitude of RAB takes the perpendicular distance. So RAB here times sine theta here is D by definition. D is RAB times sine of this angle here, sine theta. So this was equal to the couple moment, and magnitude of F times D is the couple moment. Well, yep, there's our formula. It was right. So you can always prove this formula to yourself by just calculating individual moments due to the two components of the couple, and remind yourself that that is the magnitude of the couple moment. Now it doesn't have the direction, so you would still need to get the vector direction, but that's of course just going to be the normal to the plane of the two forces, and then right hand rule. So in this case the moment due to these forces would be into the paper or clockwise. Okay, so now we've just proved that a couple moment is equal to the magnitude of each of the forces producing it times the perpendicular distance between. Something else that's really cool about what we just proved, notice there's no reference to point P. We could have put any point. It didn't have to be between the two lines of force. It could be way over here or way up here underneath the title. Doesn't matter. We just indirectly kind of proved something super important, and that is the moment of a couple about every point is the same. That is so not true of a single force. The moment of a single force is totally dependent on which point you care about, because that defines the radius. But when you have a couple moment, it's applying the same torque everywhere. So that becomes really interesting when we're applying this for conditions of equilibrium, is couples can get added in the summation with all of the different moments produced by all the different forces. It doesn't matter where they are. We just add them in by their direction and, of course, orientation. So they just get added in as a vector sum. So this is one of the benefits of sometimes doing things with a mathematical proof, is sometimes we can make observations that we can then use, and it makes our work really easy down the road. So you'll see this fact used when we go on to apply conditions of equilibrium and get the sum of the moments for a body. And we'll notice that we've got to include a given point reference for forces, but if a moment is being applied as a couple, a pure moment, it just gets added in. Okay, quick example. You got two 20-pound forces. They're being directed in the positive and negative j directions here, so they're both parallel to the y-axis. They've got what looks like a 15-inch separation, and one's going in the positive j and one's in the negative. And somebody wants to know the magnitude and the direction of the couple. So we can almost do this by observation. So 15 inches is d, it's the total separation. So we can use our F times d to get the magnitude. So we get 20 pounds times 15 inches, so 20 inch-pounds. And we know that the two couples are defining a plane that is the xy plane. And so the normal to that plane is the z-axis here. And so all that's left is to figure out if it's in the positive z or the negative z, so we can use the right-hand rule, put our fingers maybe in the direction of that positive 20-pound force and curl around into the direction of the negative 20-pound, or imagine going what would be counterclockwise around a clock whose hands are at the origin, looking down on it from the z-axis, and so we're rotating in this way around the z-axis. So the couple is actually pointing in the positive k-hat direction. So 300 inch-pounds, k-hat is the moment. And so if you had a shaft in the z direction, this would give you pure torque about your shaft. So you could spin your shaft without having to go shooting out of the bearing. And that would be good if you wanted to do that. All right, that is it for couples and a little mathematical proof. And we'll start putting these to work later on.